Unit 3, Section 6.10, Worked Examples. For the following table, compute the mass of 160 grams of radioelement D left each day if the element loses half its mass each day. What type of decay is this? On day 1, there's 160 grams. Each day it loses 1/2 of its mass. So on day 2, we'll have 1/2 left, which will be 80. On day 3, it will have 1/2 left, which will be 40. On day 4, it will have 1/2 left, which will be 20. And on day 5, it will have 10 grams left. What kind of decay is this? This is exponential decay. For the following table, compute the area of a 550 square foot shed left to paint if you paint 40 square feet a day. What kind of decay is this? So we start at 550 on day 1. How much is left to paint if we paint 40 square feet on day 1? So on day 2, what's left is 510 at the beginning of the day. And on day 3, at the beginning of the day, there's 470. And on day 4, there's 430. So each day we're subtracting 30. And on day 5, there's 390. And what kind of decay is this? This is linear. Same amount is lost each day. If Mario hired a plumber for 4 hours, the total cost would be $120. If he hired the same plumber for 11 hours, the total cost would be $260. Assume a linear relationship between the cost y in dollars and the number of hours worked x. Find an equation in slope-intercept form that models the relationship between the cost and the number of hours worked. There are several ways to work this problem. In my math lab, this is a multiple choice question. There are 4 answers provided. So first we know there are 2 points on the line that were given in the problem, 4, 120. So 4 hours cost $120 and 11 hours of work cost $260. We can find a slope using those 2 points, using the formula for slope. If I let the point 4, 120 be 0.1, the point 11, 260 be 0.2, go ahead and set up my slope formula. y2 minus y1, 260 minus 120 equals 140 in the numerator. x2 minus x1, 11 minus 4 equals 7 in the denominator. Go ahead and divide, and so I get 20. And that's actually the hourly cost for the plumber. Now we can use the slope and one of the points to find the y-intercept, and then we use what's called the point-slope formula. And in that, which is shown here, you take one of the points, y minus y1 equals m the slope times x minus x1. And remember the slope that we calculated was 20. And if I go ahead and I simplify, I'm going to get y minus 120 equals, and I distribute on the left side, 20x minus 80. And then if I add 120 to both sides, I'm going to get y equals 20x plus 40. So there's the equation of my line. Now, you can also do this another way. Once you have the slope, you can eliminate 2 of the answers that were given in the question. Here's the answers that were given, actually, because answer B doesn't make sense because it doesn't have a y-intercept. It has 2 x terms on the right side. I've got A and I can eliminate D because it doesn't have the right slope. So what I could do is check my points in equation A and in equation C and see which of those equations is correct. And in this case, of course, we come out with equation C, which is what we found using the point-slope formula. The number of a certain type of bacteria Y present in a culture is determined by the equation Y equals 3,000 times 3 raised to the x power, where x is the number of days the culture has been growing. Find the number of bacteria present after 4 days. Substitute 4 for x and solve for y. And I've put that formula down here. I'm going to pull up my calculator. And I'm going to start again with the exponent. So I'm going to take y, and I'm going to take 4, raise it to the, I'm going to take 3, raise it to the 4th power, and then multiply by the starting amount, which was 3,000. And I get 243,000 bacteria after 4 days. And notice it's tripling each day. The exponential function f of x equals 41.32 times 1.024 raised to the x power describes the population of a certain country y in millions in year x. Substitute 0 for x, find a country's population for year 0, try to do that without a calculator, and then find the population in year 24 as predicted by the function. So for the first part, why do they say I can do this without a calculator? Well, I know that any base raised to the 0 power is simply 1. And so for the first day, it's going to be simply what we started at, 41.32 million. For year 24, we're going to need our calculator. So we're going to take our base of 1.024, and we're going to raise it to the 24th power. And then we're going to multiply it by the starting population, which is 41.32 million. And we get 73.006 million. A town currently has 5,000 residents. The expected future population can be approximated by the function p of x equals 5,000 times 1.388 raised to the 0.2x, where x is the number of years in the future. Determine the expected population of the town in 10 years and in 50 years. So I've gone ahead and I've put those two values into the function. And in the first case, let's go ahead and work the first problem here. And we're going to go ahead and simplify the exponent first. So I notice I've got 0.2 times 10. So 0.2 times 10 is going to give me 2. So I'm actually going to be squaring that 1.388. So I'm going to take 1.388 and square it, and then multiply by the starting population, which was 5,000. And so I get 4, let's see, we're going to round off its people, so we're going to round off. So it's going to be 9633. So it's 9633. And then in 50 years, again, I need to simplify the exponent first. So I'm going to take 0.2 times 50. So this time my exponent is 10, so I'm going to take that base of 1.388, raise it to the 10th power, and multiply by the starting population, which was 5,000, and I get a population of 132,698.